Welcome back, and we are continuing our talks about solving systems of equations by moving into how do we recognize when a system of two equations and two variables doesn't have just one ordered pair solution. Recall that when we talked about how lines or equations of lines might interact on a graph, we said that they could intersect, or they could be parallel, or they could coincide. And so what we've been doing so far has been solving systems of equations that have two lines that intersect. Now, what we have not looked at yet is how do we know what to do when we have a system of equations that represents a system with no solution? How would we recognize that algebraically? So the picture shows us a system that will have no solution. Um, so we are going to talk about what does that look like when you're solving. All right, so if while you're solving a system, in the process of solving, both of your variables are eliminated. Okay, both x and y, if you're using a system in xy, they both disappear and you're left with a false statement. Then the system has no solution. Okay, so what does that really look like? Well, this one is pretty easy. Let's look at this example. We're going to solve this system. We've got a system where 3x plus 5y is equal to negative 16, and negative 12x minus 20y is equal to 30. We could solve this by substitution if we wanted to, but this is really set up a little bit easier to solve by elimination. And notice that if I'm just focusing on my x values here, if I multiply this top equation through by 4, I should end up with 12x over a negative 12x, which will eliminate nicely. So that's what we'll do. We'll multiply this top equation by positive 4. When we do that, we end up with 12x plus 20y is equal to negative 64. And so I keep that bottom equation as is. And so I've got a positive 12x and a negative 12x, and they are over each other right there. So when I add them together, they will cancel out. But oh my gosh, what else happens? The y's cancel out. And so when I add them together, both those x's and y's cancel, and I'm left with this statement: 0 is equal to negative 34. Now, I don't know about you, but I don't think that that's true, right? 0 is definitely not equal to negative 34. And so, since this is a false statement, we would say that this system has no solution. And you can just say no solution, or you can use the empty set symbol. This is pretty much what you would want to write, or just say no solution. So then the other type of system of equations that we would want to discuss would be a system where the lines coincide. And so recall that that is a system that has infinite solutions, right? And we would recognize this by kind of the same thing happening. You're solving the system and you're skillfully applying either substitution or elimination, and all of a sudden both variables are gone, but what you're left with is a true statement. And if you're left with a true statement, then the system has infinite solutions. Every point along each line, because they're the same line, satisfies the system. So let's look at what that looks like. So here's an example. And in this case, I've done a little bit of mischievous work because I haven't set it up to solve right away. Notice that my x's are not even over my y's, and my constants are not aligned either. So the first thing I'm going to want to do is rewrite this bottom equation so that everything is in the correct position. I'm going to move the x's, this negative 6x under this positive 2x. I'm going to move this negative 9y under this positive 3y, and I'm going to shift this negative 48 to the other side of the equal sign. So let's go ahead and do that. Okay, so that looks so much nicer. And now I'm going to examine this and think, okay, well, yeah, I could definitely use substitution here, but it does, again, look like it is a better candidate for elimination. So let's take that top equation and multiply it by 3. And when we do that, of course, that top equation will turn into 6x plus 9y is equal to negative 48. And notice that when I go ahead and add those together, everything cancels out. Everything cancels out. So I'm left with this statement, 0 is equal to 0, which is a true statement. Yay, true statement. And that means I have infinite solutions. Now, it really depends on your textbook how you express the solutions to a system that has infinite solutions. I've seen it done multiple ways. One of the ways I've seen it expressed is this way, where you write the curly braces x, y, such that, and you substitute one of your original equations in here. And what this statement is saying is, every an XY combination that satisfies this statement will satisfy the system. So that's one way that you can write it. And it doesn't matter which equation you use. But another way to write it would be to take and solve for your y variable, isolate your y. So we would do that by subtracting the 2x and then dividing out the 3. And so when we have y isolated, we can write our solution as the ordered pair xy, where the y is the expression that we solve for. And that, again, is saying for every x that I sub in, I can get a y out that will satisfy this system. So that's how you recognize systems with no solution or infinite solutions. The next thing we're going to look at is how do you solve problems, applications using systems of equations. And that's kind of where the math becomes relevant. And we will see you then. Bye.